Hello everyone, very good evening. Welcome to the interview preparation session. So let's start for the day. Yeah, so we'll just see basic statistics in the distributions. Okay, so the first question would be like, what is the difference between data analysis and machine learning? What is the difference between the analysis and the machine learning? So more of analysis of the data is what we have to do as a part of data analysis, right? We need, though you have a basic knowledge of stats, still it is good, but you should have good sound knowledge of coding part. So when we do machine learning, right, it's totally opposite of your data analysis, where you require strong knowledge of statistics is required here. So when we need to do very, very good coding, or we should have coding skills, what are the four main things we should know before studying data analysis? What are the things we should learn before we start doing data analysis? So the first one should be descriptive statistics. Second concept here is inferential statistics. Third is normal distributions or sampling distributions. Right? Finally, we should have the knowledge of hypothesis testing. Right? So definitely we all should understand the difference between descriptive statistics and inferential statistics. So what is descriptive statistics? So when you talk about descriptive statistics, it is doing exploratory data analysis, right? You have to work on the present and the past data. You describe things, right? You diagnose with the data, whatever you have. You try to pull in information so that will be useful for us for the next step of process. So it provides the exact, and we can say that it is used for describing things, right? Or to describe the data properties, right? Are covered as a part of descriptive statistics. So when we talk about the inferential statistics, right, we'll talk about them in detail, but what is inferential statistics? How it is different from descriptive? So when you're talking about the inferential statistics, here we are trying to work with a sample because we don't have enough resources to work with population data. So when we want to work with population data, okay. So when we want to work with the population data, we don't have enough resources. So what we do? We will pick up a sample, right? We pick up a sample. So this is your population data, which is denoted with capital N, out of which we pick a sample, which is denoted by small n. So whatever you have on the sample, you will generalize it to population. Right? Whatever the results you are getting on sample, which you call them as sample statistics. You work anything, you calculate a very simple calculation, whatever you do, whatever results you get on this, you generalize it and you give a statement that it is related to population. So these two should be nearly equal. Then only your sample, whatever you have picked, is an optimum sample. So selection of sample is very, very important because you are talking about population. You are giving a statement related to population, but working on sample. That is inferential statistics. We are pulling inferences from the data. So you call it as inferential statistics. The other name we can also say is that it is a sampling funnel. It just looks like a funnel, right? Different steps we follow to pick up the sample, where n is here, small n is here. It is nothing but our inferential. So where the first step holds good for population data, then you have your sampling frame. Right? It's a unique condition what you apply. The technique what you apply here for sampling, for picking up the data, sampling technique, and finally this is your sample. So results on this are generalized. These are called as I told you, sample stats. These are called as population parameters. Whatever you get on population, they are called as population parameters. Now, next, then we have to understand something about normal distribution and hypothesis testing. So someone would like to know from you, what is the difference between population and sample? Right? This is what you have to give the explanation. And then what are the most common characteristics or most common characteristics used in descriptive statistics? Most common things, common characteristics. So we can start with center, there is nothing but here first business moments. So first of all, you should understand what is the meaning of moment, right? So when we talk about moments are nothing but truths which are associated, or the facts with respect to data. You call them as moments. The first business moment is the average or the mean. Centrality. What does it capture? Centrality is what it captures. Centrality, it captures the centrality where you have mean, median, mode. Right? All three holds good. These are the common use measures. So the basic thing we all are familiar is the mean concept, which is the average of all the numbers. It is nothing but sum by total. Then you have median, right? Middlemost number of ordered data. Then you have mode, most repeated value in your data, or most occurred. Right? But the disadvantage of mode is there can be one mode, or it could be bimodal or multimodal. Right? So just because your data has some extreme values, we don't restrict ourselves with average. We just move beyond and we take mean calculation. Then you can take mode. So generally, if we talk about the categorical data is a data where no math operations, no arithmetic operations can be done, right? It's just something which you would capture as the repeated value, the most repeated category. Right? That is our can be performed, I can say. Right? So mode is used for such data. It doesn't make any sense to use mode on numeric data because it does not capture the centrality. If at all you have 23, 24, 23, 24, 25, the most repeated value, you say that mode is equal to 23. This is, if someone just capturing the centrality means you don't see whether it is mid or median or mode. They say it is 23 and it is capturing the centrality. This is the center. But moving forward and calculating the average here, average would be something else, right? So you can do it. It will not throw you any error, but it doesn't make any sense to use mode on numeric data. So preferably this is for your this. And if at all you have any extreme values in your data, this is an extreme value in your data, your average is getting affected. So what you do, you go and calculate median. Median is nothing but you either go for ascending order or descending order, whatever order you want, you'll pick the middlemost value. Okay, that is the first business moment. So whatever you get, as I told you, population parameters. Population parameters with respect to first moment is mu. Sample, you call it as X bar, right? X bar is a sample statistics, right? These two you have to remember. This is called as mu and this is called as X bar. So whatever X bar is there, it should be nearly equal to your mu. That is how we can decide that our sample is perfect sample and it is a replica of your population. Okay. Now, then moving forward, whatever you got in the first decision or first moments, we use it in our second. For getting the second moment business decision, we move and we use that mu in our second business moment decision. It's not only the average here. Average is not alone important. How the data is dispersed, right? How the data is dispersed. How is the spread? How is the spread? How is the dispersion, right? Is captured here in the second business moment decision, right? So first thing you calculate here is variance. It is nothing but the average spread of the data. It's defined as average spread of data from each data point or from center to each data point is called as variance, or average square distances of data of each data point to the center. Anyway, you can write it. Is a variance. Square root of variance gives you standard deviation. Right? They are the most commonly used measures here. So what is the formula for standard deviation? The standard deviation is nothing but first variance is given by sigma for population, and you call it as S for sample. Sigma square and sigma is standard deviation. S square and S is the standard deviation here for sample and population respectively. So now if you calculate the formula, if at all I'm doing it for population, suppose xi minus mu whole square, take the average, square root. This is nothing but your sigma. Right? If it is for the population. So this square is your variance. So average of each data point from the center or to the center, squared distance, average. Right? So this is important for us. So whatever you are getting, that is not enough. You need to even know the range. The range is nothing but maximum minus minimum value in your data set. But the important point here is when you try to compare the two values for population and for sample, xi minus mu by n whole square, right? Xi minus mu whole square by n, sigma I is equal to 1 to n. Here also I equal to 1 to n. Here it is small n. Xi minus x bar by n minus 1. So we are working with sample. Mu will be changed to x bar. N is changed to n minus 1. Now definitely it should be n. But why it is n minus 1? What is this n minus 1? So this n minus 1 is called as the degrees of freedom. Right? N minus 1 is called as degrees of freedom. It is according to the concept of inferential statistics. Right? According to the concept of inferential statistics, the point here is the results what you get on sample should be is generalized to population. To make the variance or the standard deviation of a population and sample equal, they have come up with a number which is called as n minus 1. It could be n minus 2 or n minus 3 or n minus 4 also. But this was giving the better result when compared to any other value. So they call it as degrees of freedom and they divide by n minus 1. So that your sigma square and s square are approximately equal according to the concept of inferential statistics. So not only the variance and standard deviation holds good, even for any data set, the maximum value and the minimum value is also important for analysis. So we, as I told you, whatever we are calculating as a part of first moment, now we used it here in the second moment. Right? These two. Then third, next. Third business moments help us to capture it captures symmetry, asymmetry in your data. You should write it as asymmetry. Right? It captures asymmetry in our data. Asymmetry means the shape of the data is symmetric or not. Right? Is the data the bell curve, or I can say symmetric? Or not. So symmetric means, let us draw the three different curves here. We can have, this is something which is a center equally distant from the zero. You may have like this, you may have a plot like this. This is called as a skewness, and by looking at the shape of the curves histogram, we are talking about the asymmetry. It is nothing but you call it as a skew. By looking at the shape, we are able to say that is there a skewness or not. This is also called as shape statistics. It's called as shape statistics. Right? Left skewed, the left tail is longer than your right side. Right skewed, the right tail is longer than the left side. It is giving you an idea of, is there any extreme values? How is the abnormality in your data? It's just because of your here, because of the abnormality, and this indicates a clear picture of this outliers. There is a chance of outliers in your data. Right? So these are important or not. Also, we can call them this part as a tail, and which is very, very long. You call it as a long tail. So we can never underestimate these outliers. Sometimes outliers also play a very, very important role. Right? These long tail products are also important. We can't ignore them, or we cannot delete them. We cannot, it's just like keep the outlier. It is based on the judgment, based on the remove it based on the judgment. This is a third business moment decision. So it's nothing but the expected value of x minus mu by n whole to the power of 3. 3 indicates third. Then comes the last, fourth, business moment decision. What this is going to capture? It's going to capture peak? Or then how are the tails? Are they wider tails or narrow tails, or how is the peak? And based on that, you decide whether it is platykurtic or what, like it is positive or not. So these are shape statistics. This is also called as skewness, right? And it's also it can be left or right skew. Here also it captures the peakness of the data, right? Wider peak or sharp peak. Based on the shape you are talking, this is also called as shape statistics, right? You can have a positive, you can call it, this is actually nothing but our kurtosis, right? Kurtosis can be positive, negative, and normal, or zero. Yes, no. Mesokurtic, platykurtic, right? These are the types of kurtosis. So you look at the shape, right? You look at the shape of the curve and decide to quantify it. Just by looking at the shape, you can say, but to quantify it, right, we are trying to give a number which is nothing but the kurtosis, right? It's nothing but the kurtosis. So kurtosis could be lepto, meso, or platy. And we can draw three different curves here. Okay. So first would be, right, with a sharp peak. Then I make it little bit better. Okay, a little bit better. Okay. And the other one would be very, very wider. Right? Wider. So when you have wider, flatty, normal, and meso. Sorry, this is only meso. This is lepto. This leptokurtic. Okay. So the statistical measure, right? It talks about the peaks or it talks about the stats related to, or the value related to tails or the peak, right? So the shape of the data, it measures the symmetry or asymmetry. Kurtosis determines the heaviness of the distribution of the tails. When tails also play a major role here, right? So normal distribution is something which we are interested in, right? But the point here is kurtosis, it refers to the degree of the presence of outliers. Determines the degrees of presence of outliers in the distribution. So it's a statistical measure whether the data is heavily tailed or it is light tailed in a normal distribution. So kurtosis is used to measure, it's used as a measure for financial risk, right? If at all you have a very, very large kurtosis, is associated with a high level of risk for any investment. Well, because it indicates that there are high probabilities of extremely large and extremely small returns. On the other hand, if at all you have small kurtosis, it will signal a moderate level of risk because the probabilities of the extreme returns are very, very low. But when we talk about the kurtosis, we have something called as excess kurtosis. Something which is excess kurtosis. So what is this? It is used in the stats, right? And the probability theory to compare your kurtosis coefficient with that normal distribution, right? To want to compare it with normal distribution. Excess kurtosis can be positive, negative, and 0. So whatever kurtosis value we get, we subtract it with -3 so that you can make a comparison with normal. Right? Kurtosis more than normal distribution, right, is heavy tail, which will lead to lepto, the other name. Kurtosis same as normal distribution. It's meso. There is no difference. It's just normal. Now ulta is less than normal distribution. Lighter tails or short tails, it is platy. Right? So leptokurtic is having very, very long and skinny tails. There are more chances of outliers. Right? More chances of outliers. Extreme positive kurtosis indicates that the distribution when more of numbers are located in the tails of the distribution. Leptokurtic. Right? Meso is something normal, na? Just like that. That's a normal. Meso. But platy has a lower tail. It is stretched more around the centers. Most of the data points are here only, like this. Right? So this is lepto. This is normal. This is a platy. And this talks about the 4 descriptive statistics which we are involved. Okay. Now, why do we need a 5-number summary? This is also a part of descriptive statistics. Why do we need a 5-number summary? Is it important? What is actually 5-number summary? What it is and where it is important? Why it's important? Why do we need it? Which plot will give you a 5-number summary? So first of all, what is a 5-number summary? Descriptive statistics involves an understanding of your distribution, the nature of the data. It is also a part of descriptive statistics, which consists of 5 values, and all these 5 values hold good, right? The first one is, okay, let us write it here. The minimum value. Minimum. The minimum value, right? You have then comes the 25th percentile, right? Then we have 50th percentile. We can also have 75th percentile. And finally, maximum value. Right? So this is your Q1, this is your Q2, this is your Q3. How do you calculate this 5-number summary? You will calculate the 25th percentile of your data. 50th percentile is a Q2, which is a median of your data. 75th percentile of your data. Right? So these values are helping us to describe things, and there is a function which is called as a describe function, which will give you the entire summary. Right? It gives you the entire summary. So this is related to, if at all we just do a box plot, right? We get to see the information of the 5 numbers here mentioned. So the formal way of finding out outliers is a box plot, a plot which helps us to find out outliers. The formal way is box plot, but it also gives you a 5 number summary with a minimum value, with a Q1, Q2, and Q3. This is your maximum value. An outlier is something which is existing here, means you can just get tilted, right? Something like this, right? And this region is called as IQR, which is interquartile range. Now someone may ask you, what is the benefit of box plot? You can say that yes, it gives a 5 number summary. It shows a 5 number summary, pictographical representation of 5 number summary. So it is used to even identify or compare the group of histograms. Right? Now the question comes, we are telling symmetric curve. What are the other names for symmetric curve? Symmetric curve is nothing but we have Gaussian curve or a bell curve or a normal distribution. All mean the same. Now using these 5, how do you calculate that there is abnormal situation in your data? Mention a method, okay, to find outliers. Five number summary is used here. So how it is they're going to display the outliers here? The data is something like this, right? If my model, the function gives me outliers, okay, it's a wrong diagram. Yeah, this should be good here. Yeah. So something like this, right? If it is like this, you are able to identify how is a spread, right? We are able to know how is a spread. We are also knowing that there are outliers. But how a box plot is giving you the indication that there are outliers in our data? It's taking a lower bound formula. It is restricting itself from upper bound value, right? So whatever region you have here, which is IQR, it is nothing but Q1 minus 1.5 into IQR or Q3 plus 1.5 into IQR. Q3 plus 1.5 into IQR. Anything which is less than this, anything which is greater than this, will be displayed as outliers in the form of circles. Suppose if you have on this side, yes, like this. Okay. So the formal ways to find out outliers is this, but even a histogram gives you an idea, a glimpse of that they are outliers. But how the outliers are displayed, this is how the outliers are displayed. Okay, so what is a normal distribution curve? A normal distribution is a curve which has equal symmetry across the two sides, from the positive side and the negative side. Sorry, positive side, negative, whatever. This is 0. So make it as negative, make it as positive. Right? This is a normal curve. This is a Gaussian curve. So now how do you convert? And you people should be knowing that finding out the data and if it is continuous, and if it is has to be normal, right? It has to be normal. So you check the normality, right? Either with histogram, you will check whether the data is normal or not, because it is talking about the skewness. Even with the box plot, it is talking about the spread and the outliers. You are getting an idea whether the data are normal or not. But the formal way to check whether the data is normally distributed or not, you call it as a QQ plot. And it is called as a quantile plot. Definitely, it's very important question that how do you figure out that whether data are normal or not? Is it mandatory to check whether the data are normal or not? Yes, of course it is yes, for y being continuous and the data should be normal. If the data are not normal, will sit quiet. If the data is not normal, you have to apply a technique to make it normal. Will not delete it, will not ignore it. We apply a technique which is called as a transformations. But if it is continuous, the first step you do is you have to check for QQ plot. QQ stands for quantile plot. It takes a box region of your box plot. This is your Q1, this is your Q3, and the relationship between the two, it should be linear, and the maximum data points should fall on this line. At least 50% of the data points are on the line, ignoring the other parts out of the box, ignoring this and this, but it should be linear. Linear means for any change in X, there should be change in Y, and the data point should fall on the line. If the plot it's not appearing like this, so what you have to do? You have to go and apply transformations to make it normal. Now, when you have this normal distribution, how do you convert this normal distribution to a standard distribution, standard normal distribution? How to convert normal distribution to standard normal distribution? Right? Standard how can we convert? Is there an option of converting it? Okay, the question would be like, yes, if at all you have any X happens to be a random variable, right? This is the normal distribution is characterized with two parameters, right? X tilde normal distribution with mu and sigma. X is a random variable, sigma represents distribution, n represents normality. What are most important parameters to check normality is your mu and your sigma, right? So when you convert this into a standard normal variable, it is nothing but you're measuring your X on a Z scale. If you convert this X to one Z scale, mu will become 0, standard deviation will become 1. And the formula you opt here is equal to X minus mu by sigma. And the question arises, why do you want to convert this a random variable into a standard normal variable? Because X can take any input. We want one particular standard distribution to compare any X, any random variable with one standard. X could be anything. It could be age, it could be income, it could be miles, it could be anything. All these, you will have X-axis as common, which is called as your Z scale, with mean equal to 0, sigma is equal to 1. And the scale will never change. Whatever might be the x, the scale will not change. Right? That is standard. To have a clear-cut relationship for confidence interval and all that, we will convert it, and the formula we choose is x minus mu by sigma. If x is equal to 780, mu is equal to 680, 711, like anything, right? Using z table, we will get the percentage of value. For any given x, you can calculate the probability value using z scale. Probability is something you can calculate for any x without finding any derivatives, no integrals, for any value of x. You can do that. That is our z distribution. Right? So define a confidence interval also. Z distribution is very, very important because one standard is required to compare all others. Right? So z is equal to x minus mu by sigma. So using this z, and also one more point, whenever we are talking about a bell-shaped curve, right? This bell-shaped curve, this is a center, and as we told you, mu is equal to 0. This is mean, and sigma is equal to 1. This is fixed. X could be anything. X could be anything, but your z values will fall in this range. Right? Z values will be in this range. So we'll stop here. We'll continue next week with different set of questions on stats.